Hello physics students, Mr. Steinerson here, and in this lesson I want to take a close look at finding the energy in a spring. And so we've done some problems before where you stretch a spring and you can figure out how much force is required using Hooke's law and the spring constant. But in this video I want to really break down how you can determine the amount of stored energy in a spring. Okay, so we're going to come back to using the concepts of the work-energy theorem, where it says that any work done in a system is equal to the change in energy of that system. So we're going to come back to those ideas in a second. First, though, I want to show you what we're talking about here. So going back to the PhET simulation with the spring, notice here there's a chart for energy. And it makes sense that the more I stretch something, I'm going to be storing some energy because it's going to want to bounce back. And so I want to figure out, though, what is the relationship between how much I stretch it and how much energy gets stored in. So as you can see, if I stretch this spring back, it's constantly storing in some energy. That potential energy is increasing. But I want to know, how does it increase, and is there a way that I can calculate how much energy is stored inside the spring? So that's what we're going to be taking a look at next. So to do that, we really have to go back to this idea of work and energy and how they're related. To help us illustrate this, I want to think about something different than springs for a second. So I'm going to have an example of just lifting a book off of the table. And so if we were to take a look at one of these books here and we just lift up the book off the table, let's think about the energy transformations that happen when that takes place. So for example, if I slide this book up here, I know now that I've increased that book's potential energy. So the potential energy has gone up, and it's gravitational potential energy because it's a different height off the table, right? So it had some distance that it traveled from where it was resting to now where it is, and therefore it has more energy. But here's the key when it connects with work-energy theorem. To increase that amount of energy, I had to lift the book. Therefore, there was some work done on the book, and that is exactly equal to the amount of energy that's now stored in from potential energy, the stored potential energy. So I needed to apply a force over that distance. That's the work. So force times that distance is equal to the mass times gravity times height, or the stored potential energy of that book. Okay. The similar thing can happen when we are taking a look at stretching a spring, all right? Now, when these two springs over here, both of these are at rest, and you can see they're kind of at their equilibrium spot. That's like when both of the books were at the same place on the table. I'm going to stretch one of these springs downwards, and we're going to stretch it a certain distance, all right? So I'm just going to redraw this as a stretched spring, and maybe it looks something like this. Here we go. There it is. Okay. And I also can, again, measure how far that spring has stretched. Here's my distance that it was stretched. Similarly to the book, I've also done work in this system, right? The work that was done is also equal to the amount of energy now stored in the spring as potential energy. Okay, so this is the big idea that we're going to come back to. The work done on that spring is equal to the stored potential energy of the spring. All right, so I'm going to rewrite this just slightly, and I'm going to say that the work done is equal, in this case, when we're talking about the spring, is equal to potential energy of the spring. I'll just put a little S after this so we know we're talking about this potential energy of the spring. Okay, so coming back to this idea of a book compared to a spring. Yes, we are doing work in both cases. However, the way the forces are interacting are different. So if I'm lifting a book, I am using a constant force. So I'm always lifting with the same amount of force over that entire distance. So let's say I'm lifting it up to a distance of 7, right? And if I want to figure out the amount of work done, then I'm going to take the force times that distance. All right, so in other words, I could take 5 newtons of force times my 7, and I'm going to get about 35. If it's meters, let's just say for the units, we're going to get 35 joules. Okay? Now, it doesn't matter how I multiply those things together. I could, if I really wanted to, break this into 7 smaller segments and just find out the work done in each one, and then add those all together, and I'd still get up 35. So it's still the same idea if I break it into smaller segments or if I treat it as a whole. In fact, what we're doing here is we're finding the area of that shape under the curve, right? So we're finding the area because we know work is force times distance. Okay, I'm going to take that same idea and apply it to the force of the spring. Now, remember from Hooke's law, when we're applying a force to a spring, as we stretch the spring, the force increases, and it increases at a linear rate. That's the K value in the spring constant. So we might start off with no force in the beginning, and then as we stretch it a little bit, we have a little bit of force, we keep stretching it, we get a little bit more, we get a little bit more and more and more, till we get to maybe 5 newtons of force when it's stretched that distance of 7. Now, when I take a look at both of these, we both can find work. However, what we're looking for, though, is something entirely different. If I just multiplied 5 and 7, I would get a completely wrong answer. Because if you look at this carefully, part of the force is much less than 5 newtons in the beginning, and then it only equals 5 newtons at the end. So I can't use 5 newtons as my force because it's not the same force for the whole time I'm stretching the spring. So I have to think about this slightly differently. And remember when we broke the force or the thing into small segments? We can do that here too, except my shape is slightly different. If I was to add up all these small segments to figure out the work done, I would get a triangle instead of a rectangle. So I can use the area under the curve with the area of a triangle to help me figure this out. All right, so let's do that. The work done in this case is equal to all of these segments added together in that triangle shape. So 1/2 times the base times the height. So times force times x, or the distance. All right, so in this case, if I put numbers in, I'll have 1/2 times 5 times 7. And that ends up being about 17.5 joules. A very different answer than what I would get over here because the force is not the same for the whole time that we're stretching the spring. And that's a big thing to keep in mind. Okay, so if we know that to find work, we're still doing force times distance, but this is the force to stretch the spring, then we can use that in that equation. All right, so let's go back up to the top here and think about this in terms of our work energy theorem, right? Because remember what we're ultimately trying to find is we're ultimately trying to find out a way to find that potential energy. And we know it's equal to the work done on this to stretch the spring that distance. Okay, so I have to go back to this idea. The work done to stretch the spring was actually equal to 1/2 force to stretch the spring times the distance it traveled. All right, so I can plug that in. I'll use this color here. So we have 1/2 force from the spring times x. Now that's equal to the potential energy of the spring. Okay, but if we think back to Hooke's law, Hooke's law gives us a relationship for the force of the spring. It says that force is equal to the spring constant times the x. Okay, so I can take this whole thing and I can plug it in wherever I see that force from the spring. So I'm going to do that here, 1/2. Now I'm going to have kx times x. It'll still be the same thing, and that equals the potential energy of the spring. Okay, let's simplify this one more step. And so I have 1/2 times kx squared is equal to the potential energy of that system. All right, so now I know that the energy stored in a spring, or the potential energy of a spring, is equal to 1/2 times kx squared. And this will be the relationship that we can use. Okay, I want to go back to that simulation because it was giving us some potential energy values, and I kind of want to see if that's the case. So I'm going to turn on this force plot here, and I'm going to turn on this energy marker. And as we increase the amount of displacement, as I stretch the spring backwards, watch what happens. Notice that the force and the distance are increasing at that linear rate, and this blue section is the area under the curve. What I want to do is I want to see, does that match what we could calculate for our energy over here? All right, so let's go up just a little bit higher, and let's get about let's do 170 newtons maybe. All right, so I'm going to go back just one more. There we go. Okay, so if I am using a force of 170 newtons and I pull it back 0.654 meters, I want to find out how much energy now is stored. This is telling me it's 55.6 joules. All right, so let's verify that. I'm going to come back down here and try to verify that. So if we use our equations, we know that the energy required, so work done to stretch the spring, is equal to the potential energy stored in the spring, okay? And that's equal to 1/2 kx squared, okay? So let's start with this, the 1/2 kx squared part, and in my simulation, they do give me a k value. It says 260 Newton meters, okay? So I'm gonna plug that in, 260 Newton meters. And they also give me an x value, and my x value was 0.654. All right, so I'll just put that in, 0.654. Meters, all right, and that has to be squared, okay? So I'm just solving now, plugging these numbers in quick. 4 squared. All right, and I get an answer of 55.6. This would be joules. We're measuring the potential energy of this system. Let's go back to our simulation and see what we got. Oh, there it is, 55.6 joules. Awesome. So that's one way to solve this, right? And we could also do the same thing if we were just finding the area under the curve here. All right, so let me find that out as well. So if we know that where our force is 170 newtons and our displacement, our x, is 0.654 meters, and if we're just finding the area of that, then I can go back and find the work done is equal to 1/2 times the force times the distance. In this case, 1/2 times 170 times 0.654, and let's see what that is. So 0.5 times 170 times 0.654 gets me 55.6 joules. Awesome. Those two should be the same because we're really calculating the same thing with just a slightly different angle. All right, so in summary, when we're finding the amount of work done in order to stretch a spring, we have to use the, and that's going to equal the change in the potential energy stored in that spring. And we can find that using this formula right here, 1/2 kx squared. Hopefully this overview went through how that formula is derived a little bit and in the cases that you can use it. Please reach out if you have any questions, and have a great day.